Hello friends, I, Anjali Shinde, Associate Professor, Department of Mathematics, S.V.K.T College, Diwali Camp, going to teach you about Bernoulli's equations and method to solve Bernoulli equation. In the previous lecture, we have studied how to solve linear differential equation which is first order by two methods. First one is separation of variables when the equation is homogeneous, and second one variation of parameters method when the equation is non-homogeneous. Today we are going to see how to convert a nonlinear differential equation which is not originally in separable form but can be transferred to separable form. So what is a Bernoulli equation? A equation of the form y dash plus pxy is equal to fx y raised to r, where r is not equal to 0 or 1, because when r is 0 or 1, the equation becomes linear equation. We are going to see non-linear equation. So condition on r is r should not be equal to 0 or 1. So any equation of this form 1 is known as Bernoulli equation. Now observe that this equation is not in variable separable form. So we are going to transform this to separable form using method of variation of parameter. So this can be transformed to separable form by using method of variation of parameters. For this, we start with the associated homogeneous equation of 1, that is known as complementary equation. So consider the complementary equation, that is y dash plus pxy equal to 0. Let us assume that y1 be solution of this complementary equation. If y1 is solution of this complementary equation 2, this implies that y1 satisfies this equation. So we have y1 dash plus pxy1 is equal to 0. Now let us assume that y is equal to uy1 be the required solution. Y is equal to uy1 implies that differentiating with respect to x, y dash becomes uy1 dash plus u dash y1. So substitute these values of y and y dash in equation 1. So we have y dash, that is u y1 dash plus u dash y1 plus px y is nothing but uy1 is equal to fx y raised to r, that is uy1 raised to r. Simplifying this, we get u into bracket y1 dash plus px y1 plus u dash y1 is equal to fx into u raised to r y1 raised to r. Observe that from equation 3, y1 dash plus px y1 equal to 0. So this value is 0, means we get u into 0, it becomes 0. So it remains u dash y1 is equal to fx into u raised to r into y1 raised to r. This is because of 3. So we get u dash is equal to y1 fx u raised to r y1 raised to r. Once we get variable separable form, so we have we are able to find the solution of this equation by variable separable. So once we have this equal to 0, we get an equation, reduce this to variable separable form, we get our required solution. Consider the example to get the method. So the question is, solve the following equation by Bernoulli's equation. Y dash minus y is equal to xy square. Observe that it is non-linear because of this term y square. So it is Bernoulli's equation. If it is non-linear, it is not directly variable separable, but it can be transformed to variable separable form. So we use method of variation of parameters. For that, we consider the complementary equation. So consider the complementary equation. That is y dash minus y equal to 0. That is dy by dx minus y equal to 0. Or we can write dy upon y minus dx is equal to 0. This is variable separable form, and once we get variable separable form, integrate this, we get integral dy upon y minus integral dx upon integral dx is equal to 0. We are taking constant of integration to be 0. Actually this is constant of integration. We are assuming constant of integration to be 0 in method of variation of parameter. So we get log y minus x is equal to 0, or we have log y is equal to x, or y is equal to e raised to x. We assume this solution, which is solution of the complementary equation, as y1. So let us assume that y1 is equal to e raised to x. Once we get y1, we assume that required solution is y is equal to u into y1. y1 is nothing but e raised to x. So it is u into e raised to x. Y is equal to u into e raised to x. Differentiate this with respect to x. We get y dash is equal to u into e raised to x plus u dash into e raised to x by product rule. Now substitute this y dash and y in given equation. So given equation becomes y dash, that is u e raised to x, plus u dash e raised to x minus y, that is u e raised to x, is equal to x y square, that is u e raised to x bracket square. This plus u e raised to x minus u e raised to x gets cancelled. We get u dash e raised to x is equal to x u square e raised to 2x, or simplifying we get u dash upon u square is equal to x e raised to 2x upon e raised to x, that is x e raised to x. This is nothing but variable separable form, and once we get variable separable form, integrate this. So we have integral u raised to minus 2 du is equal to integral x e raised to x dx, and therefore u raised to minus 1 upon minus 1 is equal to integrate by parts u, that is x, integral e raised to x dx minus integral derivative of x, integral e raised to x dx, that is nothing but minus 1 upon u is equal to x e raised to x minus e raised to x plus some constant c. This implies that u is nothing but minus 1 upon e raised to x common into bracket x minus 1 plus c. Once we get the value of u, we substitute in y, and therefore our required solution becomes y is equal to u into e raised to x, that is e raised to x into bracket 1 upon e raised to x into bracket x minus 1 plus c. So this is the final solution of given Bernoulli's equation. So originally the equation is not variable separable form. We consider its complementary equation, find the solution, assume that solution to be y1, and by method of variation of parameters we assume that y is equal to uy1 be the solution of the given equation. That is, you want to find u, by variable separable form we find u, and substituting u in this equation again we get y is equal to u into e raised to x. This is the general solution of Bernoulli equation. Consider the next example. Solve the following differential equation. The equation is x y square y dash is equal to y cube plus x. So we want, the given equation is 3x y square y dash is equal to y cube plus x. Now observe that our Bernoulli's equation is y dash plus pxy is equal to fx into y raised to r, where r is not equal to 0 or 1. This equation is not directly in this form, but it can be reduced. So what is this equation? This equation becomes y dash is equal to y cube upon 3xy square plus x upon 3xy square. That is, it becomes y dash is equal to 1 upon 3x into y plus 1 upon 3 y raised to minus 2, or we can write down y dash minus 1 upon 3 xy is equal to 1 upon 3 y raised to minus 2. Now observe that it is written in this form, y dash, here px is nothing but minus 1 upon 3x, fx is nothing but 1 upon 3, and r is nothing but minus 2. So this is nothing but in this form Bernoulli's equation. So this is Bernoulli equation. If you want to solve Bernoulli equation, because it is not directly in variable separable form, what we use? We use the complementary equation, solve it, find its solution, show it by y1, and then by method of variation of parameters we assume y is equal to uy1. So now we consider the complementary equation. The complementary equation is y dash minus 1 upon 3xy is equal to 0. That is dy by dx minus y upon 3x is equal to 0. Or we can write this as dy upon y minus 1 upon 3 dx upon x is equal to 0, or dy upon y is equal to 1 upon 3 dx upon x. This is variable separable form, and because it is variable separable form, integrate, taking constant of integration to be 0. So dy upon y is equal to 1 upon 3 dx upon x, that is log y is equal to 1 upon 3 log x, or we have log y is equal to log x raised to 1 by 3, and therefore y is equal to x raised to 1 by 3. Once you get value of y, assume this to be solution y1. So let y1 is equal to x raised to 1 by 3, and therefore let us consider y is equal to uy1 be the required solution. So let us assume that y is equal to u into x raised to 1 by 3. Once we have y, we differentiate this with respect to x, we get y dash. So by product rule, what is y dash? U as it is, derivative of x raised to 1 by 3, 1 by 3 x raised to minus 2 by 3 plus u dash x raised to 1 by 3. This is derivative y dash. Once we get y dash and y, we substitute this in given equation, or therefore I will consider the simple equation, that is we have rewritten this y dash minus 1 upon 3. So y dash is nothing but u into 1 by 3 x raised to minus 2 by 3 plus u dash x raised to 1 by 3, that is value of y dash, minus 1 upon 3x into y. Y is nothing but u into x raised to 1 by 3 is equal to 1 upon 3 y raised to minus 2. Now simplify this. So u upon 3 x raised to minus 2 by 3 plus u dash x raised to 1 by 3 plus minus u by 3 x raised to 1 by 3 minus 1, that is x raised to minus 2 by 3 is equal to 1 by 3 y raised to minus 2. This u by 3 x raised to minus 2 by 3 and minus u by 3 x raised to minus u by 3 gets cancelled with each other. So we get u dash x raised to 1 by 3 is equal to 1 by 3 y raised to minus 2, or what is our y? U x raised to 1 by 3. So we will put here also the value. We have y is nothing but u x raised to 1 by 3 bracket raised to minus 2. So this becomes u raised to minus 2 x raised to minus 2 by 3. So this is nothing but u dash x raised to 1 by 3 is equal to 1 by 3 u raised to minus 2 x raised to minus 2 by 3, or we have du by dx into x raised to 1 by 3 is equal to 1 by 3 u raised to minus 2 x raised to minus 2 by 3. Now we want variable separable form. So it is du upon u raised to minus 2 is equal to 1 upon 3 x raised to minus 2 by 3 dx upon x raised to 1 by 3. This implies that u raised to minus 2 becomes u square du is equal to 1 upon 3 x raised to minus 2 by 3 minus 1 by 3, that is x raised to minus 3 by 3, that is x raised to minus 1 dx, that is nothing but u square du is equal to 1 upon 3 dx upon x. Now this is variable separable form, so integrate. Integrating we get integral u square du is equal to 1 by 3 integral dx upon x. It is nothing but u cube upon 3 is equal to 1 by 3 log x plus c, or I will say c dash. This implies that multiplying by 3 we get u cube is equal to log x plus 3c dash. I will take c as constant plus 3c dash. So multiply throughout by 3, we get the constant 3c dash, assume it to be equal to c. So we get u cube is equal to log x plus c, or u is equal to log x plus c raised to 1 by 3. Once we get value of u, we substitute that value in y, and therefore we get the last solution, that is the solution becomes y is equal to log x plus c raised to 1 by 3 into x raised to 1 by 3. This is the total solution, or we have x into log x plus c raised to 1 by 3 is equal to y, or we get y cube is equal to x log x plus c. So this is the final solution of Bernoulli's equation. So though originally the equation is not in the form, we are able to rewrite the equation in Bernoulli's form and able to solve it by method of variation of parameters. We transform it to variable separable form, and integrating we get our required solution. We will take one more example to get the idea. Solve the differential, Bernoulli's differential equation. X, y, y dash is equal to 3x raised to 6 plus 6y square. Originally it is not in the form y dash plus pxy is equal to fx into y raised to r. So we have to rewrite in this form. So I will write down, we divide by xy, y dash becomes 3x raised to 6 upon xy plus 6y square upon xy. So y dash becomes 3x raised to 5 into 1 upon y plus 6 upon x y, that is y dash minus 6 upon xy is equal to 3x raised to 5 y raised to minus 1. Now this is in the form where r is nothing but minus 1, px is minus 6 by x, and fx is 3x raised to 5. So now it is written in Bernoulli's. To solve this equation, though it is not variable separable, we will transform this variable separable by considering the method of variation of parameters. So consider the corresponding complementary equation. What is corresponding complementary equation? Y dash minus 6 by xy is equal to 0. That is dy by dx minus 6y upon x is equal to 0, or dy upon y minus 6 dx upon x is equal to 0. Integrate, because this is variable separable form, and once we get variable separable form, we integrate this. So integral dy upon y minus 6 integral dx upon x is equal to constant. We are considering the constant to be 0. So we get log y minus 6 log x is equal to 0, or log y is equal to log x raised to 6, or y is equal to x raised to 6. This is solution of complementary equation. We assume this solution as y1. So let us assume that y1 is equal to x raised to 6. And the consider last solution, that is y is equal to u into y1, or we have y is equal to u into value of y1 is x raised to 6. So we assume that our last solution y is u into x raised to 6. Now once you get this, we want to find value of u. So differentiate this with respect to x. We get y dash is equal to u into 6x raised to 5u plus u dash into x raised to 6. Now put y and y dash in equation. So we substitute this here. We have substituting in 1. So we get 6u x raised to 5u minus 6 by x, value of y is u x raised to 6 is equal to 3x raised to 5u y raised to minus 1, that is u x raised to 6 bracket raised to minus 1. Simplify this. Therefore we get 6u x raised to 5u minus 6u x raised to 5u is equal to 3x raised to 5u value of y is this 6u x raised to 5u plus u dash x raised to 6, this is value of y dash, minus 6 by x, value of y comes to be u x raised to 6 is equal to 3 x raised to 5u, and value of y comes to be u x raised to 6 raised to minus 1. Simplify this. So we get 6 u x raised to 5u plus u dash x raised to 6 minus 6u x raised to 5u is equal to 3 u raised to minus 1, x raised to minus 6 into x raised to 5u becomes x raised to minus 1. This 6u x raised to 5u and minus 6u x raised to 5u gets cancelled. So we get u dash x raised to 6 is equal to 3 upon ux, that is du by dx into x raised to 6 is equal to 3 upon ux, or u du is equal to 3 dx upon x raised to 6 into x becomes x raised to 7. So we write down this as variable separable form. And once we get variable separable form, u variables together and x variables together, so this is variable separable form, we integrate this. So integrate. Integral u du is equal to 3 integral dx upon x raised to 7, or integral u du is equal to 3 integral x raised to minus 7 dx, that is nothing but u square by 2 is equal to 3 x raised to minus 6 upon minus 6 plus constant of integration. We get u square is equal to 2 into 3 minus 1 by 2 x raised to minus 6 plus some constant c dash, or we have u square is equal to 2 gets cancelled minus 1 upon x raised to 6 plus 2c dash. I assume 2c dash is equal to c is another constant. So 2c dash is equal to c is the another constant. This is value of u square, or simply we get u is equal to root of minus 1 upon x raised to 6 plus c. Once we get value of u, we are able to put this value in y, and therefore our solution becomes y is equal to u is nothing but root of minus 1 upon x raised to 6 plus c into x raised to 6. So this is final solution of Bernoulli's equation. So observe that any Bernoulli's equation is always of the form y dash plus pxy is equal to fx into y raised to r, where r is not equal to 0 or 1, because if r is 0 or 1, it becomes linear. To solve non-linear differential equation, what we are using? We are taking method of variation of parameters, that is, we start with complementary equation. Its solution is denoted by y1, and once we get our value of y1, we find the last solution, that is y is equal to u into y1. By substituting y is equal to u into y1 and taking its derivative y dash, the given differential equation converts to variable separable form, and integrating that variable separable form, we get value of u. Substituting that value of u in y, we get our final solution. So this is nothing but Bernoulli's method and Bernoulli's equation and method to solve that Bernoulli's equation. In next lecture, we will study homogeneous differential equation. Thank you.